Welcome back to another explainer. Today, we aren't just looking at some boring textbook formula. Nope. We are going to frame a legendary chemical equation as an epic hero's journey. You know, it's easy to think of molecules as just static little dots floating around in a beaker, but at an industrial scale, they actually undergo these monumental, dramatic transformations. So get ready for an action-packed adventure into what chemists call Dow's process. I mean, really think about it for a second. How does a tough, completely unyielding molecule actually transform its entire identity? This right here is our call to adventure. Just imagine the sheer, overwhelming force it takes to literally rip away a foundational piece of a sturdy chemical's core and replace it with something completely new. It doesn't happen easily, and it for sure doesn't happen gently. It takes an epic molecular quest.
Chapter 1, Meet Our Hero, Chlorobenzene.
Okay, let's dive into this. Now, this might look like your standard dry chemical equation map, but look a little closer. If you read it from left to right, this is actually a full-blown, action-packed storyline. It outlines the exact trials, the specific enemies, and the ultimate transformation our molecule has to undergo to reach its final form. So, our starting hero is a molecule named chlorobenzene. Look at its structure for a second. It features this really tough, hexagonal ring of carbon atoms. Think of it like a tiny knight wielding a massive, indestructible shield. And gripping super tightly to the top of that shield is a single chlorine atom, represented by the Cl. Our hero is sturdy, stable, and completely ready for an industrial-scale adventure. But chlorobenzene isn't meant to just stay that way forever. The finish line of this quest, the ultimate transformed state our hero is desperately trying to reach, is a highly useful molecule called phenol. Do you notice the difference? The tough shield is still there, but the chlorine is completely gone. In its place, our hero is now holding an OH group. That single, tiny swap absolutely changes what this molecule can do out in the real world.
Chapter 2, Trial by Fire and Pressure.
Before we go any further, we really need to shatter a common misconception here. When we hear the word chemistry, we almost always picture a scientist in a white lab coat gently swirling two colorful liquids together in a little glass beaker. Well, the reality of industrial preparation? It is nothing like that. It requires extreme, aggressive brute force. Our hero molecule is about to face some serious elemental trauma. And nothing brilliantly illustrates the sheer scale of that brute force quite like this number: 320 atmospheres. That's the intense pressure required just for the first step. To put that into perspective, being under 320 atmospheres of pressure is basically like being crushed near the very bottom of the deep ocean. It's this immense squeezing weight that's deliberately designed to force molecules together that otherwise would never, ever interact. But get this, pressure alone isn't going to cut it. We also need 623 Kelvin, that is blistering heat. It's the equivalent of being trapped inside a massive industrial-scale pressure cooker. This intense combination of 623 Kelvin and 320 atmospheres of pressure provides the massive energy required to physically shatter chlorobenzene's tough, stubborn bonds. Let's actually pause and reflect on that for a second. Try to imagine the incredible physical stress those atoms are under right now. The extreme heat is making them vibrate violently, while that deep ocean pressure is just crushing them together, and right at the absolute peak of this stress, an opposing force, two molecules of sodium hydroxide, or 2NaOH, charges right into the fray. This is literal molecular warfare. Chapter 3, The Intermediate, Sodium Phenoxide. Let's introduce a crucial vocabulary word right here: intermediate. In chemistry, an intermediate is basically a vulnerable halfway there phase. So our hero has survived that massive initial trial, but it isn't quite finished transforming yet. Our hero is now what we call sodium phenoxide, and it's wearing an ONA group. But remember, this is just a temporary resting state. It's a brief pause before the final hurdle. It's definitely not the ultimate goal.
So, what exactly was lost in that first major battle? Let's mechanically break it down. Step 1. Chlorobenzene faced the 2NaOH under all that extreme heat and pressure. Step 2. During that massive clash, a molecule of salt, NaCl, was knocked away, right along with a molecule of water, H2O. Step 3. Shedding those parts, our hero basically stumbles out of the pressure cooker as the intermediate we just talked about, sodium phenoxide.
Chapter 4, The Final Acid Test. Let's move to and see how this builds toward the finale. Our totally vulnerable intermediate, sodium phenoxide, now faces a sudden splash of dilute HCl, that's hydrochloric acid. This acts as the final catalyst.
This acidic splash literally shocks the molecule into dropping its one last piece of baggage, another molecule of salt, NaCl. With that final piece gone, the sodium is replaced by hydrogen, and our hero officially emerges fully transformed. It is now phenol.
Chapter 5. Future Careers in Chemistry.
Now, we can actually take this incredible micro-level chemical equation and apply it directly to the macro-level real world. I mean, why do we even put molecules through these epic quests? Well, because human society depends on the results. People actually do this for a living. Chemical engineers are the brilliant masterminds who design these massive hero journeys at an industrial scale. They're the ones building the giant titanium pressure cookers that can safely withstand 320 atmospheres in 623 Kelvin. They calculate the exact amounts of NaOH and HCl needed to maximize the yield of phenol. Designing these extreme reactions is a real, vital, and highly impactful career choice.
Chapter 6. The Explainer Quiz. All right, time to test your memory. Question 1. Think back to the sheer brute force needed to break chlorobenzene's bonds. What were the two extreme numbers, specifically the temperature and the pressure, that our hero faced in that very first trial? Say it out loud if you know it. Do you remember? It was 623 Kelvin and 320 atmospheres.
Okay, question 2. After surviving the 2 NaOH attack and dropping salt and water, our hero entered a halfway point. What is the specific chemical name of that vulnerable intermediate molecule featuring the ONA group? Got a guess? That's right, it's sodium phenoxide. And our final question. To reach the ultimate goal, our intermediate needed one last shock to drop the final NaCl molecule. What final reagent acted as the catalyst to completely finish the transformation into phenol? Think about it. Did you get it? It was a splash of dilute HCl.
So the absolute most crucial takeaway here is that behind every material, every medicine, and every plastic we use on a daily basis, there is an incredible, invisible story of transformation taking place. The modern world is literally built on these epic molecular journeys. Now that you know the extremes required to shape the building blocks of our universe, the real question is, what will you engineer next? Thanks so much for joining me on this explainer, and keep questioning.